Hello everyone, so thanks for the organization of this event. So I'm going to present a joint work with Lucas, who's at NYU now, and Nicolas on gradient flow dynamics of shallow ReLU networks. So this work focused on the training of two-layer ReLU neural networks for regression tasks with gradient descent. And for this problem, actually, there is still a big mystery on the theoretical side. And in particular, we still have these three questions which remain largely unanswered. So in theory, so do these neural networks converge to zero training loss? Do they show some simplicity bias? And what is the role played by initialization? So for these different questions, we only have partial answers yet, and either assuming large initialization, classification tasks, or infinite width networks. And so in this work, we focus on small initialization, regression tasks, and finite width networks. But for that, to have a tractable analysis, we need to assume orthogonal data, which is the main assumption of our work. I'm going to discuss about it. And also what is good with this orthogonal data setup is, so first we can give a complete answer to these questions, and also we can describe completely the dynamics of the training. So the setting is the following. So we have n data points, and the goal is to minimize the square loss because we are in a regression setup. And so we have a parameterization of our network as two layers. So the aj here corresponds to the weights of the output layers, while the wj corresponds to the weights of the hidden layer. And we have a ReLU activation function. And as I said, the main assumption is that our inputs are orthonormal. So the fact that they are of norm 1 is not important here. But the fact that we assume then they are orthogonal is a big assumption, and because we need it actually to make the analysis tractable. But still, we can see it as an approximation of what happens when we are in a large dimension setup where the dimension d of the data is much larger than the number of data points n. And also, we are analyzing the gradient flow, which can be seen as a continuous approximation of gradient descent when we make the step size going to 0, because then it's easier to analyze using differential equation tools, for example. So as I said, initialization plays a key role. And so in our setting, we assume that we initialize the hidden layers following a Gaussian initialization with a scale of initialization lambda that will be very small in our setting. And also we consider a balanced initialization where the output layer absolute value is the same as the norm of the hidden layer. And so this balancedness will be kept all along the trajectory, making the analysis much simpler as well. And we need to assume something on the initialization. So this is a deterministic condition here, but actually it requires, so it holds with high probability when we have a very large number of neurons in our network. So for example, exponential number of neurons in the number of data points. And so basically just assume that at initialization, we have at least one neuron in some cone of our space RD, and also at least one neuron in some cone of our space, some other neuron in another cone of the space RD. And so when we have all of this, we have the following main theorem, is that when the scale of initialization is small enough, then the gradient flow will converge to some interpolator, meaning that the training loss will converge to 0. And moreover, we have some implicit bias towards minimal norm interpolator when the scale of initialization converges to 0. So as I said, we have two results. So training loss goes to 0, and also some implicit bias towards some minimal norm interpolator. So we have also many other insights that can be difficult for the proof. So I cannot present all of them, but the main one being that we are able to characterize precisely the training dynamics. So here, so I'm considering data points of 2 points of dimension d because I need them to be orthogonal, so I need 2 points. And so here the second dimension corresponds to the bias parameter of the neural network. And so the green points are the 2 data points. The green line is my estimation function at each time. And each blue star is one neuron of my neural network. And so its x value is given by the position of the kink of the ReLU, and its y value corresponds to the output weight layer for this neuron. And so what happens is that we did identify several phases during the training. So during the first phase, what happens is that all the neurons will stay small in norm. So our estimation function won't change, but these neurons will align towards some key directions that will be crucial for the remaining. So here you see that the align towards 2 directions. Then there is a first phase where one of these cluster of neurons will grow in norm until fitting all the positive labels. It could be also the negative. And then the third phase where the same happens, but with the other labels, so the negative one here. And this is what we describe for the exact dynamics. So to summarize, we are able to give complete descriptions of the training dynamics for orthogonal inputs. And also we are able to give a training loss convergence result, some implicit biased result, and also at some point we observe an intermediate non-trivial saddle point during the training, so I didn't discuss about it. And these three results are actually conjectured in the general case. So we are able to prove it for the orthogonal case, and we hope that it can help us to understand better the general case. And so if you want to know more about this, come and talk at the poster session. Thank you.